Hey, and welcome to our lesson on logarithmic properties. Now, we started this the other day in class. We didn't quite finish it. So take notes on your own paper and pause the video when I ask you to work some problems. Try them yourself before you see how I approach these problems. And at the end of the video, we have a little special thing to show you, a little proof as to why at least one of these properties works. So throughout the video, I want you to remember our two major themes about logarithms. Theme number one, logarithms are exponents. Every time you see a logarithm, you can think of it in terms of an exponent. And number two, logarithms kind of suck. They can kind of be really hard to think about. So whenever you hit that brick wall in your thinking, remember logarithms are exponents. And you can always convert from logarithmic to exponential notation to get yourself through some of the challenging products. So first property I want to look at is the product property. And as you may recall, the product property says anytime you take a logarithm of a product, that is equal to the sum of each separate logarithm. Similarly, the quotient property, anytime you take a logarithm of a quotient or a division problem, that is equal to the difference of the separate logarithms. But the one we didn't quite get to is this power property. And this, to me, is one of the most powerful, powerful properties of logarithms. And that is anytime you have an exponent inside a logarithm like we have here, the power property lets us take that exponent and bring it on down with everybody else. It looks like this. That exponent can come down and join the rest of the group. And you know how tricky exponents can be. And if we can get them down with all the other numbers, we're going to be able to work a lot of math. And a lot of the problems we solve will involve using this power property. And then, of course, at last, we have what's called the equality or the one-to-one property of logarithms. In this class, we call it the property. Because if log base b of m is equal to log base b of n, then clearly m and n have to be equal. So initially what we're going to do is we're just going to use these properties to manipulate logarithms for the sake of manipulating them. These are definitely pre-calculus skills. These are things that we're going to be seeing later on in pre-calculus. In calculus, they're just skills that we have to have when working with logarithms. You will kind of get to see how effective they are next year. But there are times where I want to take a statement that has a lot of different logarithms and I want to condense it into one single logarithmic expression. So let's just dive in and take a look at problem 1 here. Problem 1 right here. Notice I have a log base 4 to the left and log base 4 to the right. And what I want to do is I want to condense this into a single logarithm. So first of all, before I join the logarithms together, I notice there's a 3 out in front and there's a 2 out in front. So my first move is I'm going to do the reverse of the power property. Normally we bring powers down with logarithms. Now I'm going to take these powers and move them up. So the first thing I want to do is get these powers, these multipliers out in front, up as powers. And this becomes log base 4 of x to the third plus log base 4 of y to the second. And now you'll notice I'm adding two logarithms. And when you add separate logarithms, this is the product property, I can take a logarithm of their products. So this becomes, in a single logarithm, log base 4 of x cubed times y squared. Now that you've seen this, why don't you try number 2 on your own? Pause the video and see if you can do it. Okay, welcome back. I hope you tried it. Again, before I do anything, I need to take this exponent and move it up here. And remember, this exponent 4 is going to affect this entire quantity. Same with this exponent of a 2. I'm going to move it right up there. So after I just move my exponents, I end up, in this case, getting the natural log of x minus 4 to the 4th. Remember that 4, it affects the entire, whatever is inside that logarithm. minus the natural log of x squared. Anytime you subtract separate logarithms, that becomes a division problem, and there you go. You do not have to expand x minus 4 to the fourth. You don't have to multiply x minus 4 times itself 4 times. Just use the exponent there. But this is the final condensed answer. Let's keep going. Let's try this one here. 1/5 times the quantity. Notice these brackets. I'm multiplying the entire thing. So if you want to follow the order of operations here, you can clean up what's inside the brackets. The product property means we're going to take this x times this x minus 2 and get x squared minus 2x. And now, if we're following the order of operations, we can take this 1/5 and bring it up here as the exponent. And we end up getting log base 3 of x squared minus 2x, all to the 1/5, or the 5th root. I think you're going to find in higher level math that rational exponents are kind of easier than roots, than radical symbols. And one last one, this last one can be a little tricky here. I'd like to write this entire expression with all 4 terms, this entire expression as a single logarithm. So first of all, notice this is log base 2, this is log base 2, this is log base 2, this is not. And what I want to do is I want to see if I can write the number 3 as a logarithm with a base of 2. So off to the side, I'm going to do some side work. And again, that side work is, can I write 3 as log base 2 of something? Well, remember our theme of logarithms. Logarithms are exponents, and they're hard to think logarithmically. So if you're looking at this and you can't think about what the question mark is, convert it. Convert it into exponential notation. 2 is my base. My exponent is 3. And that has to equal the question mark. And so the question mark is 8. And so over here, how do I write 3 as a log base 2 of something? It's simply log base 2 of 8. And all these other logarithms just come right down, except you'll notice I did use my power property here to take this 5 and move it on up. Now, let's handle this left to right. So this is the product property. It's log base 2 of 8x. And I'm just going to bring these down. Let's continue working from left to right. I see the quotient property here. Anytime you have subtraction of separate logarithms, that's a division problem. And I'm just going to bring this log base 2 of z to the 5th. Again, anytime you have subtraction of separate logarithms, that's a division problem. And this whole process on this page was condensing. We were taking a big, long expression and trying to squeeze it together into a single logarithmic expression. And if we condense, well, the reverse of that has to be true. We might have times we want to expand. And so in this next section, we're going to take the single logarithmic expression and break it apart into a series of adding or subtracting of different logarithmic expressions. So let's see if we can take these examples and expand them, starting with the first one. So this is a log. Notice there's no base, so the inferred base is 10. It's the common log of 3x squared y. So you might use the product property to expand this out. And I think there's one more thing we can do. Of course, we can use the power property to grab this 2, which is only affecting the x, and bring it on down with everybody else. And this becomes log base 3 of 2 log 10 plus log of y. Let's keep going. Let's try number 6. Ooh, a natural log. Okay. Now, the temptation we're fighting here is the temptation to do too much. We're going to take this as far as we're allowed to take it, and the trouble is students want to take it even further, and you can't. So first of all, notice the quotient property. So I'm going to separate these logarithms by subtraction. Second of all, I see a radical. Well, that's just an exponent. So if I rewrite this radical as a 1/2 power, you'll see I have one more thing I can do, and that's that I can grab this exponent and bring it down with everybody else, and we end up with that. Now, I know what you're tempted to do. What you're tempted to do is to distribute this logarithm, but it's not a number, it's a function, and you cannot distribute functions. This is as far as this thing can be taken. You can't go any further with it. You're done. You have to fight the temptation to distribute non-numbers. You can only distribute numbers. Finally, here's one last problem. Log base 2 of 32 times the quantity x squared minus 4. Again, you might see that the product property here. You might see that we have multiplication, so we could separate this out into log base 2 of 32 plus log base 2 of x squared minus 4. Log base 2 of 30, wait a minute, 32, isn't 32 a power of 2? So if we rewrite this as log base 2 of 2 to the 5th, and then x squared minus 4, we could factor that. Now over here, by golly, we can use this power property and bring that thing down. And over here, we could use the product property. So let's see what we end up with here. This is 5 times log base 2 of 2. And then the product property, we could take the separate logarithms. Now again, avoid doing too much. You know what log base 2 of 2 is. That is just a 1. So over here, we get a 5. And over here, you have to fight the urge to distribute. You are not allowed to distribute those logarithms, so it just stays like that. Now, this last page has some heavy math in it. I told you that we could kind of go through and prove one of these properties. Let me go ahead. I'm going to show you this pretty intense math. If you can follow it, great. If you can't follow it, that's okay. But just try to follow. Don't take notes. Just try to follow. So let's prove the product property. I mean, we don't have time to prove all of them. We'll just prove one. So let's show that log base b of a product is equal to log base b plus log base b of n. Just the logarithms are separate sums. So first thing I'm going to do is I'm going to just assign a variable to log base b of m and a different variable to log base b of n. I'm just bringing in two new variables to represent these giant expressions. And using our definition of logarithms, we can say b, the base, to the exponent, x equals m, and b to the y equals n. So let's take a look at this part inside, m times n. If we look at m times n, we know that m times n, according to this definition over here, m is b to the x, n is b to the y. And using our definition of logarithm, using our exponent rules, we get that this is b to the x plus y. So anytime I multiply m times n, we know that's the exact same as b raised to the x plus y. So let's take this statement right down here, this one here, and let's take log base b of both sides. So log base b of the left side equals log base b of the right side. And look at the right side over here. Isn't that just x plus y? And up here, we know what x is, and we know what y is. And when I make these substitutions, when I replace x with log base b of m, and I replace y up here with log base b of n, that's what I get. And that's the proof of one of these logarithmic properties. And you'll notice the proofs involve us coming back to exponents. Because what are logarithms? They're exponents.